Hello students, and welcome back for our third and final video of this week on pericyclic reactions and conjugated pi bond systems. When we left off last time, we were talking about cycloaddition reactions, a type of pericyclic reaction, and we discussed these in the context of molecular orbitals and how these reactions must conserve the symmetry of the molecular orbitals. Now we're going to move on to the two other pericyclic reactions, the electrocyclic reactions and sigmatropic rearrangements. And we're also going to talk about the way light interacts with conjugated pi bond systems. So let's begin by redefining electrocyclic reactions. So electrocyclic reaction is a pericyclic reaction where conjugated polyene undergoes a cyclization, and in the process we lose one pi bond. So you can see we go from 3 pi bonds here to 2 pi bonds, and we gain a sigma bond. Now we have another sigma bond right here that wasn't there before. And here's that case here with a 6-membered ring. Here's a electrocyclic reaction with a 4-membered ring. So then overall we have, again, 1 pi bond lost, 1 sigma bond made. Now there's a variety of ways in which these electrocyclic reactions can go. First of all, we saw in the cycloaddition reactions that by interacting the molecule with light, we can promote an electron to a new molecular orbital, changing our highest occupied molecular orbital to one that is one higher in energy. And so we saw how having the interaction of UV light with these compounds can affect the way that they react. And that's also going to be true for electrocyclic reactions. So we can see here as an example that if we have here an this molecule here undergoing an electrocyclic reaction, if that is in the presence of UV light, we will get a resulting trans configuration on our methyl groups here that are the substituents at the end when this ring closes. However, if this is undergone under heat, just normal conditions, no light, just heat, and by heat, it doesn't have to be extremely hot. It just means not a bunch of UV light changing the result of this reaction, because it's changing the energy, the highest and lowest unoccupied molecular orbitals, because an electron is promoted. But if this reaction is undergone with this isomer here, so you can see the difference between these isomers too. Here the methyl groups are on the outer edges, right? Here the methyl groups are kind of like both on this top edge. And so if we have this isomer, which is a different isomer than this one because of the position of this methyl group, this will produce the trans isomer of the closed ring under heated conditions, meaning no light, basically. However, if we want to produce the cis closed ring here, where the methyl groups appear on both sides, we can take this isomer and have it undergo this reaction under conditions with UV light. However, if there is no UV light and we have this isomer, it will react. Basically, just one more time, if we have this isomer, if we have light, it will produce a trans isomer of the closed ring. No light, it will produce a cis isomer. We have this isomer of this molecule. Under light conditions, it will produce a cis isomer of the closed ring. Under no light conditions, just normal heat temperature, basically, it will produce the trans isomer. This is also true in this simpler example here. So we have 2 pi bonds in this one. And if we expose this isomer, where the methyl groups are located on this outer regions here, to light, it will produce the cis isomer of the closed ring here. However, if we have no light, it will produce a trans isomer. Likewise, if we have this other isomer, note the difference here. This guy is now in this position, the downward position. It will produce the trans isomer in the presence of light, and without light, it will produce a cis isomer. And this can be explained like some of the cycloaddition reactions. This can be explained in terms of the conservation of orbital symmetry. So going back here to our first example, where we had the methyl groups on the outside here on this triene, under the conditions of heat, we're going to get the cis isomer. But if we have the other isomer here, where this methyl group is not pointing outward here, it's pointing inward, that will, under heat, produce the trans isomer. And again, we don't need particularly hot conditions. Often room temperature, sometimes even below room temperature, is enough to make this. We're just saying that this is happening without the need for UV light. So recall from our previous lecture that, and I can quickly go back to that just to show you. If we look here for the cyclohexatriene, so I'm quickly going through these. Sorry about that. Just trying to get to cyclohexatriene here. Let's see. Well, just referring to, there's a large diagram in the book you can refer to as well. But the lowest energy cyclohexatriene here would have all of these orbitals aligned. The next lowest energy orbital would have one node, and as you know, as we go up energy levels, we get one more node in the molecular orbitals each time. So on the third lowest energy level, we have two nodes here, and in these two nodes, we have the the 6 pi electron containing carbons here. We got an overlap here on this node here. We have an overlap here, and we have an overlap here. And of course, this goes in terms of these ones on the edge being in the same orientation, the one on the outside being reversed. That's the only possibility right now. That's what's producing these nodes, is that this is in the opposite direction of these two on the side. So if we look at the way this would be arranged in a ring, the red nodes here would be aligned here, and the blue nodes would be aligned. And so in order for this to close, and for these orbitals now to produce a sigma bond, they're going to have to directly overlap, because that's what a sigma bond is. And so there's going to be a kind of turning that occurs that will put these lobes into a direct overlap. And that turning is going to happen in such a way that the red lobes turn and overlap, or the blue lobes turn and overlap. And in either case, this is going to be the same type of rotation, where both of these have to rotate in opposite directions. This is going to be what's called disrotatory rotation, disrotatory reaction. So what we mean by disrotatory is that these two lobes must turn in opposite directions. Here, the left lobe here, turning in the counterclockwise direction, while the right lobe is turning in the clockwise direction. You can kind of visualize this here with your hands. So we've got both these methyl groups that are on the outside, and if we do disrotatory, that means that we're going to rotate our hands in opposite directions. So instead of our hands going in this same direction like this, they're going to go in opposite directions. So you can use your thumbs, for example, to represent here the methyls. They're sticking outward. And then when we rotate disrotatory, it's either going to go like this, or it's going to go in the opposite direction, which I can't turn. But either way, our methyl groups are going to end up in the same position and in this disrotatory rotation. And this is going to result in a cis type of stereoisomer at the end. And so when you're thinking about this, you see 6 pi electrons. When you see 6 pi electrons, you should think the lobes on the outside are going to be aligned. They've got two nodes here, so it has to go from one direction to the other direction to the same direction. So with 6 pi electrons, like 3 double bonds basically, alternating with single bonds, you're going to have lobes that are in the same direction. So they're going to have to rotate in a disrotatory fashion. And your hands can really help with that. It can also help with visualizing where the lobes have to go. So if I'm putting my thumbs like where the lobes go, okay, I know this is 6 pi electrons. These lobes are going to be aligned. So when they rotate, they must rotate in a disrotatory way to overlap. Then I can use my thumbs again and say, okay, I'm looking at this example. The methyl groups are pointing outward. If I rotate my hands disrotatory in opposite rotational directions, once I'm done, they will end up both in the same direction, or cis, like this. And so your hands, maybe you'll be doing this on the exam, your hands can be a useful mnemonic for this type of rotation if you know how to use them. Now, when it comes to a system with 4 pi electrons, basically alternating double, single, double, just 2 double bonds, you're going to have 4 overall molecular orbitals. In the lowest energy molecular orbital, recall that all of these will be aligned all the way across. The next lowest orbital will be the highest occupied molecular orbital, in which there will be one node. And so these lobes will be positioned in opposite directions of one another. And so under thermal conditions without any light, what's going to occur is, well, first, if you look at the lobes, now they're pointing in opposite directions, right? So now I'm going to do this with the lobes, not with the methyls. So in order for the same sign of lobe to overlap, we're going to have to rotate both hands in the same direction. See how we're rotating them both? In my case, from my perspective, I'm rotating them both clockwise. And then I have the overlap. So now I do the same thing, and I know that I'm going to have to go and this is going to be called conrotary in the same direction, right? Now I point my hands out like they're methyls, and I'm going to have to rotate in the same direction. So rotate them both in the same direction, and I'm going to get anti-position. I know that's kind of hard to do with your hands, but you'll get the anti-position. And so the result of this, when we rotate, again, so because the lobes are beginning in opposite directions, we're going to have to rotate them in the same rotational direction, conrotary, like this. And when it comes to the methyls, again, we're going to rotate in the same direction, conrotary. So we end up with the methyls pointing opposite directions. So under thermal conditions, for a 6-pi electron system, we're going to get the syn, or the same side configuration, the cis configuration. But for a 4-pi electron system like this, we're going to get the anti-result on these substitution groups in the 4-pi electron system due to the conrotary rotation. Both will rotate clockwise or counterclockwise and yield the trans product. So this is a summary of that. Under thermal conditions, conjugated systems with 6-pi electrons will undergo a disrotary rotation. Conjugated systems with 4-pi electrons will undergo a conrotary rotation. Now here we're looking again at the highest occupied molecular orbital for a 6-pi electron system. And again, remember that when you have 6-pi electrons, you'll have 6 molecular orbitals that are created from those 6 p orbitals. These 6 molecular orbitals, the lowest energy will have all these nodes aligned. The second lowest will have 3 aligned and 3 aligned and a node. And then the next will have 2 nodes with 2 aligned, 2 aligned, 2 aligned. And so when they have 2, 2, 2 like this, they're going to start off in the same direction. Now, however, if we take a 6-pi electron system like this and we shoot it with UV light, we're going to promote the electron to the next higher molecular orbital, and that will become the highest occupied molecular orbital. And so now we'll go to the next higher molecular orbital, which is one that has, instead of 2 nodes, 3 nodes. So in these 3 nodes, we're going to have 2 sets of these p orbitals. They're not really p orbitals, right? They're meant to describe molecular orbitals, but they will overlap. But on the ends here, these 2 lobes will be positioned in opposite directions. And so we can see this is a completely different situation now. When the ring closes, these are starting in opposite directions. So whereas before they were the same direction under thermal conditions and underwent a disrotary rotation, now they're in opposite directions on the end, and so when the ring closes, they're going to undergo a conrotary rotation. So we can see here, again, under heat, our lobes end up in the same direction for the 6-pi electron system, so they undergo disrotary. Under light, now they're in opposite directions, they're going to undergo conrotary rotation. And for the first example, because they're cis, we have a molecular symmetry right along the center here. So although we have these 2 chiral centers, this complex is meso, this compound is meso, and so that's why it does not have an enantiomer. But here we have one that now they're trans to one another. Now we no longer have that symmetry, and so there's going to be 2 enantiomers, where this is dash and this is wedge, or the other one where this is wedge right here and this is dash. So note the result though again. So in the heat conditions, we have our methyls out. We undergo a disrotary rotation and they end up in the same direction. However, if we have the promotion, now it's going to be the opposite. It's going to undergo a conrotary rotation. So they're going to rotate in the same direction. They're going to give you one up and one down. And that's going to be this situation here. And don't forget that this one is not meso. So also we can do the rotation in the opposite direction and get the other isomer. We have a similar thing in the case with 4 pi electrons. It's just the opposite. Remember, when we have 4 pi electrons, without any light, the highest occupied molecular orbital will have those 2 lobes unaligned, so an opposite direction. And so under heat conditions, to close the ring, they'll have to undergo a conrotary rotation, same direction they're rotating, to close up. But if now we excite the electron, now it's going to change to the next molecular orbital here, and now those lobes will be aligned. And so they're going to want to close up. They're going to have to go rotate in the opposite direction for a disrotary rotation. And the result, now you can do that with the methyls. So we've got our methyls pointing out. If we're under heat, we're undergoing a conrotary rotation, same direction. They're going to go opposite, and they're going to have a trans product. However, if these methyls are sticking out the way they are here, I'm using my thumbs to show they're sticking out. If they're sticking out like this, and we have light, it's going to undergo a disrotary rotation where they rotate in opposite directions, so one clockwise, one counterclockwise, both in the cis position. And like before, we have a plane of symmetry here in this molecule. So although it has 2 chiral centers here and here, it is meso, and so there's no enantiomer. But here, this does not have that same plane of symmetry, so there is an enantiomer. The enantiomer would be this one, where now this guy, this guy is a wedge, not a dash. This one. And so to summarize, these are the so-called Woodward-Hoffmann rules. If we have a 4 pi electron system undergoing an electrocyclic reaction, under thermal conditions, it will undergo conrotary rotation. Under photochemical conditions, using light, photochemical means exposing it to light to initiate the reaction, it will undergo a disrotary. For 6 pi electrons, it is the opposite. Under thermal conditions, disrotary rotation. Under photochemical conditions, conrotary. So that's electrocyclic reactions. Now let's move on to sigmatropic rearrangements. This is our last pericyclic reactions that we'll discuss. It's one in which we do not lose a pi bond or gain a sigma bond. Essentially what we do is we break a sigma bond and we make a new sigma bond somewhere else, and the pi bonds that were somewhere move over. Location of the pi bonds will change. So here, in terms of the mechanistic arrows, you can see it's the same type of thing. It's all in going concerted fashion. So these pi electrons go into making the sigma bond. These pi electrons make a new pi bond here. These pi electrons make a new here, and that completes the reaction all at once. No intermediates. So in terms of the way we describe these, there's several ways in which these can happen. And we have a notation for describing the way in which they happen. So in the example that we just looked at, while this is occurring, we have a transition state where there's a partial single bond here that is shown here that is beginning to form. We have a single bond that's partially lost now. This is partially broken. And then we have pi bonds that are partially forming here, partially lost here, partially forming here, partially lost here. And so these partially created and lost bonds are indicated by these dots. And the way the notation works is it is written as the number of carbon atoms on one side of where the sigma bond is broken. So here, 3 carbon atoms on this side, and here the number of carbon atoms between the sigma bond that's being broken, the sigma bond that's being formed on the bottom here. So there are 3 carbons on this side between the sigma bond broken and the sigma bond formed. There are 3 carbons here on this side between the sigma bond broken and the sigma bond formed. So we call this a 3-3 sigmatropic rearrangement. Now, as I mentioned, there are other potential rearrangements. So here we have another type of sigmatropic rearrangement that can occur when the bond here is to hydrogen. So we have the same type of arrangement here. This sigma bond is breaking. We're going to make a new sigma bond right here. And so that's indicated by a dotted line here for this bond partially broken and a dotted line here for this sigma bond partially formed. Now these pi electrons are starting to move over here. So we have kind of like half a pi bond here, half a pi bond here. These pi electrons are starting to move over here. So we have like half a pi bond here, half a pi bond here. And this is what's referred to as a 1-5 sigmatropic arrangement, because there are 5 the sigma bonds that are being broken here and formed here. There's only 1 atom between them on this side. It's the hydrogen atom. But on the other side, there are 5 carbon atoms. And so this is what would be called a 1-5 sigmatropic rearrangement. Another type of sigmatropic rearrangement is a so-called Cope rearrangement, which is another type of 3-3 sigmatropic reaction, but it's one in which all the 6 atoms in the cyclic transition state are carbon atoms. So it's a specific. It is a more specific form. So is this a Cope rearrangement? Yes, it is, because all 6 carbon atoms involved are all 6 atoms involved are carbon atoms. So here's another example of a sigmatropic rearrangement, 3-3. It's the first one was called the Cope rearrangement. This is just another example. It's a Cope rearrangement, but this is meant to show that sometimes when it's not completely symmetrical all the way around, there will be a preferred product to this rearrangement here. Like in this case here, we're undergoing a 3-3 cyclic rearrangement here, sigmatropic rearrangement. And we have these pi electrons creating a sigma bond here, these pi electrons moving over here, this sigma bond being broken, and now we have a pi bond over here. And so the resulting product here we have will be produced at a significant amount here relative to the reactant. The reason is because the product has a lot more or significantly more thermodynamic stability. This is due to the fact that these pi bonds here that at the beginning are each singly substituted, meaning they are only attached to 1 other carbon each. However, in the product, this double bond here is doubly substituted. And we know that more substituted alkenes are more stable. And so this product produces a more stable molecule with more substituted alkenes on it. And so the equilibrium here will favor the more substituted alkenes produced. When we have a 3-3 sigmatropic rearrangement in which one or more of the atoms is oxygen here, and we have an oxygen atom here, this is what's referred to as a Claisen rearrangement. And the Claisen rearrangement occurs when we have an oxygen here, an ether, so we can see there's an ether, there's an oxygen between 2 carbon atoms, and the ether, it has a vinyl group on one side, meaning it's directly attached to the carbon that's in a double bond, and there's an allylic group on the other side, meaning the oxygen is attached to a carbon that is attached to the carbon. It's going to be the same type of reaction mechanism arrows here. Again, we have the vinylic group here, the allylic group here. On the vinylic group, the pi electrons here go into creating the new sigma bond. On the allylic group, those pi electrons go into moving the double bond over here. And finally, the sigma bond is broken between the carbon and the oxygen, and that goes into a pi bond between the carbon and the oxygen, ultimately producing a carbon-oxygen double bond, which is extremely thermodynamically stable relative to a carbon-oxygen single bond, or even relative to a carbon-carbon double bond, due to this difference in electronegativity here. So we get ultimately a significantly more stable molecule having the carbon-oxygen bond. And so the equilibrium will favor the formation of the carbon-oxygen double bond as a result of Claisen. This can also occur with allylic and aryl ethers. So aryl means that it's attached to a benzene ring. And so here we have an example of that. This ether here, this oxygen attached to two carbons, it's an ether. On one side, we have an aryl group, the oxygen directly attached to the benzene ring. On the other side, we have an allylic group, the oxygen attached to one carbon, one carbon away from the double bond. And the notation here is the same. We have here these pi electrons on the vinylic group are going to go into making a sigma bond here between these two carbon atoms. The pi bond here in the benzene ring is going to go into making a pi bond with the oxygen. And finally, the sigma bond between the oxygen and carbon are broken here, producing a pi bond over here. However, this molecule is not going to stay in this formation because the benzene ring has fantastic stability due to the resonance of the electrons all the way around the ring. So all these carbons are sp2 hybridized in this benzene ring. So we have 6 pi electrons that can just flow and flow and flow around this ring, really stabilizing that molecule. And so that stability has been lost, though. The stability of that aromatic ring with the movement of the pi bond to being between the carbon and the oxygen. So ultimately what happens is that there's a jump of a hydrogen, and that hydrogen is essentially going to jump over here and end up on the oxygen. And we're going to have the pi bond recovered here between for the aromatic ring. So we have this aromatic ring recovered, and we recover that stability. So this is going to greatly favor the tautomerization of the ketone. So you may remember from the alkyne chapter, when we did the hydration of alkynes, we would get enols, which would tautomerize to a ketone or an aldehyde, to a carbonyl. This goes the opposite direction, actually. It tautomerizes from the carbonyl to the alcohol and to the enol. And the reason is it's not a real enol. It's actually a phenol, which has this fantastic stability of the aromatic ring. And so that extra stability has it favor the phenol rather than the ketone here. Also, these types of reactions occur in nature, in biology. For example, you may have heard that you can get vitamin D by drinking milk because it's been fortified with vitamin D usually, or you can actually go outside and your body will make vitamin D. And it will make vitamin D from steroid hormones that you have, and from this is like cholesterol analog. So you can recognize steroid hormones because they have this unique 6-ring, 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 5-ring structure. When you expose your skin to UV light, that will promote an electrocyclic reaction. In that electrocyclic reaction, we have a movement of these pi electrons here and the breaking of this sigma bond to produce another pi bond, and that opens the ring. And then that can undergo a sigmatropic rearrangement here, where the hydrogen atom moves over, the pi electrons then each move over here, and ultimately we get the structure of vitamin D. It's a 1-7, 1, the 1 here being the hydrogen atom, the 7 being 1, 2, 3, 4, 5, 6, 7 carbon atoms. We get a 1-7 sigmatropic rearrangement, which ultimately produces our vitamin D. And so these reactions aren't just some weird thing that doesn't relate to you or anything you're studying. If you're studying medicine or biology and taking this class, why do I have to take OChem? It's important to understand the way the body works. This is one of the important ways the body works. Our bodies operate by the same organic chemistry rules that you're learning now, for example, in the synthesis of vitamin D. Finally, we're going to talk about the interaction of pi bond systems with UV light. Now, an interesting feature of molecules with extended conjugated pi bond systems that I highlighted in the first slide is that these molecules that have extended conjugated pi bond systems will actually absorb visible light and have a color, which is interesting because we have basically two ways of having molecules that have color. One is if they have a transition metal in them, and that's something you learn about in general chemistry, transition metal complexes. The other is if they have extended pi bond systems. which ultimately change the energy between the molecular orbitals. The more conjugated pi bonds there are, the closer the energy of these molecular orbitals become, and ultimately they go from being in the UV range, higher energy, to a lower energy that is in the visible range, and then visible light will be absorbed and you will actually see a color. So a lot of our clothes use these types of organic dyes rather than transition metal complexes. Usually a lot of paints and stuff use transition metal complexes. So compounds with conjugated pi bond systems absorb UV or visible light. This occurs because you have these molecular orbitals that we talked about before, and you can shine light at these and they will promote the electron if that light is in just the right wavelength of energy that represents the difference in energy here between these two orbitals. So in general, the necessary energy to excite an electron from the pi to the pi star, or the HOMO from the LUMO. This is kind of a notation for HOMO and LUMO, pi to pi star. Usually this is in the UV range, unless there becomes a very large extended pi bond system. Then that energy gets smaller and smaller, and it ends up lying in the visible range. And so UV-vis spectroscopy can give structural information about molecules. Specifically, it can tell us the extent to which we have conjugated pi bond systems. How many electrons do we have essentially involved in our pi bond system? This is done by measuring the absorbance, and it can be given by this formula, the log of the intensity initially shown at the molecule divided by the intensity that is ultimately left over after. And so we can see here that this is an absorption spectrum. We have different wavelengths of light, these ones being 200 nanometers, so they're in the UV range. So with butadiene, it will absorb at a wavelength of 217 nanometers, which is in the UV range. The visible range doesn't start till about 400 nanometers, and so we're still too low for that. Remember, the formulas for UV light, energy is directly proportional to frequency, which is new, and the speed of light, which is 3 times 10 to the 8th meters per second, is equal to the wavelength of light times the frequency. And so what this means is that the frequency is proportional to 1 over the wavelength, or it equals c over the wavelength. So it's proportional to 1 over the wavelength. And so a shorter wavelength is a smaller wavelength is a higher frequency, which is higher energy. So if we want a lower energy, we'll have to have a higher wavelength. So you can see here that if we have a longer and a more extended pi bond system here with more molecular orbitals, now the energy between these molecular orbitals will be even lower, and so the wavelength of maximum absorption here will be an even higher wavelength of lower energy light. If we have 8 molecular orbitals here, an extended pi bond system involving 8 carbon atoms here, this would have even smaller differences in energy between the orbitals, so the light absorbed would be even lower in energy, meaning it would be longer in wavelength, which for this cyclooctatetraene here, 1, 2, 1, 3, 5, 7, cyclooctatriene, or sorry, so 1, 3, 5, 7 tetraene. Oh my god, let me just write it. I'm having trouble saying it. 1, 2, 3, 4, 5, 6, 7, 8. 1, 3, 5, 7. Octa, or 8 carbons. Tetraene, for 4 double bonds. Tetraene. This will have even lower energy difference between these orbitals. Thus, will absorb at an even higher wavelength. So if we keep doing this and we have more and more and more extended pi bond systems, eventually these will begin to absorb in the visible region. So we call the parts of the molecule that have extended pi bond systems, we call these the chromophore. Other parts that are not part of the extended pi bond system, these are referred to as the oxochromes. And there were some people in the past that developed rules to estimate the wavelength mass depending on how many pi electrons are involved in the chromophore here. So we start with 1,3-butadiene. Its wavelength of maximum absorption is 217 nanometers. For each additional double bond in the extended pi bond system, we will add 30 to the wavelength max. So for example, here we've got 2 additional pi bonds, so we add 60 to 217 here. And we get a wavelength of max absorption is 277. Now this isn't perfect. The actual wavelength of maximum absorption is 290, but it's a good, simple estimate, basically. For each oxochromic group, we'll add 5 to the wavelength max. So in this example here, it's like 1,3-butadiene, but it has 3 oxophores right here. So the main 1,3-butadiene is like right here, 1, 2, 3, 4, and then these are the oxophores right here. There's 3 of them, so we add 3 times 5 to 217, and we get 232 net. We also have here this situation where we have a diene that is in a cyclic, but it's right on the outside of the ring, an exocyclic diene here. So for an exocyclic diene, we get a little bit higher absorbance here. This is 217 is for the base, so that's just for 1,3-butadiene. But we have an exocyclic double bond here, and so we add 5 for this one, so this is going to be plus 5. And then we have these 2 oxophores, this carbon and this carbon, which are attached to the double bond. So that adds another plus 5 for this one, plus 5 for this one. So that's a total of 15 we're adding. So 217 plus 15 is 232. Finally, if we have a diene here, and both double bonds are contained in one ring, so they're locked in this S-cis conformation, this is going to add 39 to our wavelength of max absorption. In addition, we have to consider the oxophores. So these are all the carbon atoms that are attached directly to the double bond here. So we have 1 there. Here we have, on this double bond, we have 1 here and 1 here. Then on this side of the double bond, we have 1 here. Here we have none. And so we're going to have 4 of these oxophores. So we'll have 4 times 5 equals 20 added to the 217, plus another 39 because we have this homoannular diene, the diene within the ring here in an S-cis conformation. We add another 39 and we can estimate the wavelength of maximum absorption at 276. Now you can see these aren't perfect. The actual observed wavelength max is 269, but they're, for most practical purposes, close enough. Now, why do we care about this? Again, we have all these organic dyes that we use to dye our clothes and do things, but also we have organic compounds in our food that contain these conjugated pi bond systems and themselves have colors. So, for example, this compound lycopene, which is a component of tomatoes, has a red color due to this extended conjugated pi bond system that goes across this entire part of the molecule here. And this is the reason why tomatoes are red, is because of this molecule right here, this chromophore. When it comes to carrots, carrots have this molecule here called beta carotene, which has a very, very long extended conjugated pi bond system too. Notice that this is red. That's the lowest energy of visible light. And then next would be orange. So you can see that this is a little bit longer. It has, so if we count these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 conjugated pi bonds. For the beta carotene, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 as well. It absorbs a little bit. It's like reddish orange, right? A little bit higher energy light with the orange color. And this is due to the extra oxophores here. A lot more oxophores on the beta carotene, so that adds just a little bit here. Whoops, not that one, this one. But anyway, it's because of these extended pi bond systems that these components have colors, which is what gives us our fruits and vegetables. They're nice colors. Now, it's important to note that the color that you observed is the opposite of the color that's absorbed. So whatever light is absorbed, it's what you don't see. So here, for example, this is the lowest energy UV visible light, but that's actually what is not absorbed. If we look at this color, we're going to see that what's actually absorbed is green. So if we look at this, this is going to be red. It appears red, but what that means is that it absorbs green, right? It absorbs green, okay? So it's absorbing green. It appears red. Now the beta carotene, it appears orange, right? It appears orange, which means that it absorbs blue, a little bit higher energy light, as I said, because of those two chromophores. Absorbs blue, a little bit higher energy than the green light that is absorbed by the lycopene. Finally, another application of all of this to real life, real biology, the reasons why those of you in life sciences, why am I studying so much chemistry? Actually, our vision operates off of principles associated with this too. Our interaction of our retina with light. When the so our vision is, our eyeballs here have photosensitive receptors, different types. Some are called rods, which do not detect color, but they allow you to see better in dim lighting, and cones, which are responsible for the detection of color. Now, the light sensitivity in rods, the way that it works is that you have a retinol, and this extended conjugated pi bond system is attached to a certain protein called opsin in the molecule. And what happens is when the light hits one of these double bonds, what will happen is it will promote the double bond, and sometimes it will allow for a rotation along one of these double bonds. And when that occurs, then that's how you end up detecting light. Is that rearrangement, that changing from the S trans conformation to the S6 conformation, involved with the and attached to this protein here. That gives a sensitivity for the light in your eyes. And so I hope, here's a few more here. So you know how they say that you should have beta carotene, you should have vitamin A, it's good for your eyes. It's because these are what are involved in the production of the retinol. They come from these. So if you basically chop this in half, it reacts and it ends up making vitamin A. And the retinol is in a close analog here to the vitamin A, as you can see. So when the rhodopsin is excited photochemically, a change in shape occurs. It releases calcium ions. The calcium ions block channels through which sodium ions are traveling. The decrease of the sodium ion flow accumulates, sends a nerve impulse to the brain, and tells us, oh, our molecule has sensed light here. That's the operation of the cones. And it's very sensitive. It only takes a few photons to activate, not those cones, rather those rods. Here's the structure of the protein again. This interaction of this light, it's going to cause a change in the shape. And your book doesn't go into as much detail, I think, but it's the flipping of one of these bonds here, the rotation, because that light promotes it. And so I hope that this has been interesting to you, and at the end here, giving you a little context on this, on why you might want to know more about this. I will mention that regarding these numbers here, I will ask him to use them on the exam, but I will provide them to you. So all these numbers will be provided to you. That's not something you have to worry about on the exam. I hope this has been useful, and this is the last video of the week, so I hope you have a great week studying, and I will see you guys again soon. Have a